Hi class, this is part 1 of image classification. This is the one that is going to use a fully connected neural network. We will be using these example images from the NMIST database, and the reason we're able to use a fully connected network in this example is because the data size is very small for the inputs. So you can see that they are 28 by 28. So right now I'm over here on Jupyter Notebooks. This one happens to be on the PIT system here. I'm just going to rename this one here so we know which is which. This one is going to be the fully connected one. So to get started, we'll go ahead and just import TensorFlow. One of the things you can do is display your TensorFlow version. If you want to do that, you can do it's just TF or whatever you make the alias, and then double underscore version double underscore. Okay, so once that's done, you can just take a look at your version here. My version is 2.3.1. Couple other helpers that we'll need are going to be, of course, Matplotlib, and specifically PyPlot and NumPy. I'm going to put a couple of markdown pieces in here just for documentation. So this is the fully connected neural net. So what I can do is just change this thing to markdown right here. And what you can do is just add some markdown like this. Now, if you want it to be a little bit bold, there are tags you can put on. You can see that here. So I'll put a link to a couple places, or just one place where you can find some markdown help right here if you want to learn more about it. All right, so the first thing we have to do is do some of the data gathering and preparing the data. So I'm going to go ahead and put a little comment right here for this section. So we're going to import the MNIST database, and you can do that right from Keras. So we can see it's just tensorflow.keras.datasets.mnist, and that's going to go ahead and get the 28 by 28 images for us. You can see on this website here that it has 60,000 samples for the training. So 60,000 of them are marked to be part of the training data set. Additional 10,000 of them are marked to be for the test set. And then, of course, we would want to introduce a brand new one that is never seen before. Okay, and this is right on that URL shown. It's paperswithcode.com. So here in Python, we can just load up the MNIST data set with a load data function here. And what we want to do is assign this to one to be a training set and one to be the test set. So I'm just going to call this one xtrain and ytrain. And this one's going to be called xtest and ytest. Just like that. And that should load it up okay. Or not. Oh, I forgot an equal sign. Okay, so there we go. So as a sanity check, probably one thing we want to do is just look at the images, maybe plot it out, maybe look at the raw data here. So I will just put another little markdown thing here. Let me put 2 of these since it's a subheading. Okay. So I'm just picking item number 300. I just picked it out of the blue. So we can just do plot or plt.mshow, and then you can pick one of the examples to look at. I'm looking at training example 300. So this is just example number. Okay, and let's see what number it is. It looks like an 8. Okay, and of course you can, change these around and pick a different one. Another 7. There's a 1 and so forth. So there we have it. So I'll put that back to 300. Something else you can do is just plot the raw data, or print the raw data, I'm sorry. So to do that, we can just do this, just print it. I did, what I do, xtrain 300 like this. So looking at this data, you can kind of tell that it looks like an 8 here. You can kind of make it out here, right there. The spacing isn't perfect. You can see over here it kind of wraps over, but in any case, we have a pretty good sanity check. This is showing with default color schemes, so one of the things you might want to do is just show it as grayscale, and it'll look a little bit better like this. We still want to do the same function call, but you can actually pass in a color map, and this one's going to be a binary color map here, and that's just going to essentially show it as grayscale. CMap, sorry, I keep forgetting equal signs. Okay, so you can see that one looks a little bit better. And something else we're going to want to do is, you can see right here that this data is 0 to 255. It's going to work out better with the numbers to go ahead and normalize that down 0 to 1. All right, so to normalize this data between 0 and 1, there's a lot of ways you can do it. You could probably just divide each number by 255. That would be fine. But here, we will just use another util. It's keras.utils.normalize. And we'll do our xtrain. And we'll do that. And let me just repeat this for the y. So it'll look like this. I'm sorry, not for the y. Sorry, for the test data. My fault. So this should be x test. Like that. All right, so what we want to do is just look at the data again. I'll just print it. So we should get kind of the same thing, except it should have values 0 through 1. So here's that item 300 again. And that looks pretty good. So that pretty much does it for the data loading and preparing part. The next part would be to build some kind of model. So We are going to use the easy, most common sequential model. A good old standby here. Okay. And what we need to do, I'm going to see if I can insert an image in here for you. So we have everything stored in a matrix now, like this. So this is like an example matrix. Of course, our numbers, we have a pretty big matrix here. You can see it. So what we want to do is take a matrix and just unwrap it, or we call it flattening, so that each of these cells is going to just be in a linear matrix like that, and that's going to become the inputs into our model. So to do that, we do a little bit of reshaping magic here. We can just do this. We can say Keras dot models dot layers dot flatten. All right, so let me fix this. We don't have a models in here. Okay, so get rid of this thing here that says models. Okay, too much copy and paste errors, so there we have it. And that should flatten out okay. So I'll put a couple notes here. I'll put it in Markdown. We have a 28 by 28, so we have 784 inputs, and that is our old 28 by 28 matrix here. With the input flattened. Okay. Whoops. So what we need to do is add some hidden layers, and what I'm going to do now, I'm going to put 128 in the first hidden layer. And also 128 in the second hidden layer. Oops. And then our output layer, we just have 0 through 9, so that's 10 outputs, so we have 10 in our output layer. Oops, so that should be marked down. Okay, so to do this, what we have to do is add each of these. So we'll do model.add tf.keras.layers, and then we're going to put a normal dense layer in 128. Our activation is going to be ReLU. Okay, so this would be our first hidden layer. And then let me copy and paste this for the second hidden layer. Now you have to be careful here. If I run this line again, I'm actually going to add 2 more, and I already ran it once, so I would have 3 total. So you have to be careful going back and editing these things. So you can see if I would run this again, I'll show you what this will look like here. Okay, I'll show this right when we're done adding these layers here. So let me add the output layer here. So I'll just keep it in here. Okay, so we're going to add our output layer. So we have to add another one. So same thing here. We still have a layer. It's still a normal dense layer, except there's 10 outputs. And since this is the last part of our network, we want to just have a softmax layer. Okay, so this would be our output layer. And again, I keep running this over and over again. Okay, so let's see. Let me show you a couple things here. So we can do this model.compile. Optimizer, of course, you know I'm going to pick Atom. For the loss function, I'm going to use sparse, categorical. And then we want to make sure we look at metrics. Now, one of the things you have to remember is that the input to this is actually a list. So we can't just put accuracy. We can get a lot of metrics, but we want to make sure we have accuracy. My kid keeps coughing. So let me go ahead and just run this thing here. Okay, so compile the model. If I do this model.summary, whoops, I didn't mean to do that. I meant to do that. I actually have to do a couple more things first. What we have to do, we have to build this thing first if you want to get summary information about it. So we would want to do model.build, and then you have to pass in the input shape, which I showed right down here. The easiest way to get it is just to put the input shape in like that, and then we should be able to do model.summary. And you can see all these layers, right? These extra layers in here. And that's because I kept running this thing right here over and over again. So if I run that again, then compile it. I can't do a summary here. Let me get rid of that. And then I build it, and then I do a summary again. I have even more in here, right? So this is definitely not the way this network should look. So if you would make any changes to the model, you'd probably want to make sure that you go back up here and start running this again to reset it. So here I can just make a new model. Okay, this is just news it up right there. Now I can add my flatten layer in. These are just markup lines. Now this is adding only 3 layers right there. I can compile it. This is, well, that's nothing now. Then I can build it, and now I can look at this summary, and now this looks better, right? So if I would happen to go and add, run this line again, and then run that again, and then run it again. This is this one right here, right? You can see that I'm going to end up getting something really wonky here. Okay, when we look at this. So this is not what we want. So I'll go ahead and put it back so we're all good. Okay, I should have this below here as well. I'll fix that. Okay, so I have a optimizer here. I must have hit an A. Okay, so that's better. There we have that. There. Now that looks good. So I'll just run through what I have so far. I'll zoom it in a little bit in case it's hard to see on the screen. So importing TensorFlow, just showing the version there. Grabbing matplotlib in NumPy, grabbing the NMIS dataset, loading the MNIST dataset. Just a sanity check here on displaying one of the samples, showing the raw data of a sample, and you can kind of make out an 8 here. Then what we want to do is convert this to grayscale. I'm sorry, just print it as grayscale, sorry, instead of these default colors. And now we're going to, let's see, this would be normalizing it so the data is between 0 and 1. And then let's see, the next thing is where we just left off, creating a model. flattening the input, so turning a matrix into a single array, or it's actually just a one-dimensional matrix. Okay, then we have our layers being added right here. Compile it, then build it, and then show a summary, and that looks good. And now what we have to do is continue on with the actual fitting here. So I'll do a model.fit. I'll do the X train as the input there, and X train as our comparison, and we're just going to do 3 epochs right now, and we'll see how accurate we can get. And right now I am running on a GPU. It's an A100, so we'll see how long this takes. So it took a couple seconds, and right now you should get somewhere around 95-97% accuracy here, so that's pretty good. Of course, we could run it again, and it could be a little bit different. Okay. All right, so let's take a look at what these numbers mean right here. So during each iteration, we should see the accuracy increase here for us. And we do see that, and the loss should decrease for us. If we don't see that, then we possibly have some overfitting issues or underfitting issues. We want to make sure that our network is generalizing these rules and not memorizing these rules. So what we can do is take a look at a couple more metrics here, and we can go ahead and let's do this. We're going to look at the loss and the accuracy. Oops. And this would be against the test data. Okay, so we did the training data. Now we're going to look at the test data pairs. Let's see. Okay, so that's not how you spell evaluate. That's how you spell evaluate. Okay, so right now we are about 97% accurate, which is pretty close to what the accuracy was of just our training data. So our training data was able to be passed through again, you know, on itself, essentially at 97% accuracy. And these, which we pretend it never saw before, were able to be classified 97% of the time. Okay, if you want to see what the these individuals are here, we could just put a print statement, say here's the loss, right? And we can put another one and see that it's just stored right here what the accuracy is, right? So if you know the way Python allows you to do multiple variable assignments in the same line like that. At this point, I of course could run this for more epochs. I could bump this up to you know, maybe 5. I of course could add some more layers if I'm trying to get more accurate, although it may or may not be useful. So I would have to go and reinitialize the model at this point and run everything again. Okay, and we can take a look here. and see if we get anything that's much better. Maybe slightly. Okay. Yep, looks like we're 98-ish instead of 97, or closer to 99. Okay, so that's pretty good. So on this GPU, it seems to save pretty quickly. One of the things we might want to do is to actually save the model as a file. So I'll show you how to do that. What you can do is just do model.save, give it a name. I'll call this is connected, image fully connected. And then when I run this, a file should appear over here, hopefully. We'll see what happens. Oh, it looks like I have a deprecated method here, but it seemed to work. Anyway, we can see it right here. It did save, so that's good. Let's see. So if you wanted to read this in, so if we were working with this and we wanted to work with this already trained model, what I would probably do is I would probably have something in the comments that says, you know, the model is getting loaded here. Okay. And what we would probably want to do is only start executing code here, because you can imagine if this took, you know, hours, if this took hours to run or something, we would not want to keep running this over and over again. We just want to jump down here and use our saved model. So to load it, what we would want to do, I'll just call it like, I don't know, model read in or something. And you can just read it in like such, model.keras.models.load model. And then it's whatever you put here. And that should read that in. Okay, so this would be our good starting point if we don't want to have to relearn again. So I'm just kind of saving the same one I'm loading the one I just saved. Now, you know, this is good and all, but you know, how do we actually make a prediction or something, or pick one of these to see how good it works? What you would want to do is something like this. You can just make a variable predictions and just use whatever you save this as, model read in dot predict. Now you can go and predict all of them if you want to, like that, and then it runs all of these through your model, right? Feeds it forward and comes up with a list of predictions that would look something like this. Oops. And of course, this is pretty ugly. So, and it's not even showing you all the data, but this is essentially the raw one hot outputs. Okay, and that's not in a very user-friendly looking form, and you can't even see all of them at once. Okay, so what might be better is to just try one of the predictions or something like that. So we can use NumPy, and we're just going to do predictions, or I'm sorry, argmax predictions. We'll just take the first one. Okay, and it says, all right, it says, I think the first one is a 7. Now, how are we supposed to know if it's right? Well, of course, we could look at the labeled data here. So, of course, we could automate this, and it's essentially going back, looking at this, you know, accuracy up here. But if we want to look for ourselves, we can just print, what did I do? This would be the test data, sub-zero, sub-zero. Sorry, it's plot.mshow. Plot.mshow x up. Sorry, this should look like this. Sorry, it says plot.mshow. Okay, so there's a 7, and that looks like a 7 to me. And then you can just kind of pick some random ones if you'd like to. So item sub 20 is a 9. Let's see if it looks like a 9. Yep, looks like a 9 to me. And this could almost be mistaken for a 7, but it does have a loop there, and this is, it was classified okay. Again, just pick a couple. There's a 6, right? There's a 6, right? We can look at just different ones here, right? There's a 1. So this is a fully connected neural network classifying these images on a pixel by pixel basis. We can see that it works quite well. However, it's not going to be good for big images. These images are relatively tiny. We saw that it's only 28 by 28. So the data is very small. Each input was really represented. I mean, it was represented with a byte originally, but now it's converted to a float, so it's a little bit more than a byte. But the floating points help keep our numbers from getting too large in a network. But in any case, just 784 inputs is pretty small. When we get into something with more resolution, of course, a fully connected neural net is not going to be the answer. So we would want to use a CNN, a convolutional neural network, and we'll look at that next.